All right, everyone. We have the pleasure of having Fabio Acero from CEA Satellite today. Fabio graduated from Satellite again in 2008, and he was working with John there on the extended sources, specifically remnants. Then he did a postdoctoral fellowship at Montpellier, and then he went to Goddard for a NASA postdoctoral fellowship. And that's where I met him, actually. And then he took one of these super precious CNRS positions in France in 2014. And just to give you a little bit of idea, French government actually has 4 of these positions every year, so they're extremely hard to get and very valuable. So he beat me on that one.
Those are the positions where you have no duties, no technical duties, no history duties.
Right, so these are 100% science jobs, so they're extremely good deals. And so he is actually very impressive. I was looking at his research resume today. He can analyze any high energy photon from KeV to TeVs and mostly expanding sources.
Except integral. I haven't tried this one yet.
He has some special feelings for integral for some reason. And he recently developed this novel method to analyze high spatial resolution observations of extended sources, and he will tell us how we can actually take advantage of deep Chandra and Lynx observations also in the future. With this, I will leave the floor to Fabio.
Okay, thank you for the introduction. And first, I would like to thank the organizer for the invitation and going to spend the week here. And already I've discussed with several of you, and it's going to be a fruitful week of discussion. And I'm looking forward after the talk to have discussions with also many of you during this week. So the idea here is to try to show you what we have been working. Some of the work presented here is the work by Adrien, a PhD student of mine working on the method. And so we have started 2 years ago, and right now we have submitted the methodology paper in which we test the method with Monte Carlo, and this is what I'm going to show you after. But first, so as Ezra said, I've been working mostly on extended source, pulsar-wind nebula, supernova remnants across the spectrum with Chandra, XMM, Fermi-LAT, and HESS, and I'm involved in CTA also right now. And just to give you an idea, this is RxJ 1713, one of the bright X-ray source. It's one of the brightest TeV supernova remnants, and here is shown in KeV, GeV, and TeV. And also, so I've been currently working on, we got a large program on with XMM on RxJ 1713, and this is the brand new mosaic that has been extended here in coverage and in depth, and it's a total of 800 kiloseconds, and we really can see now some faint features going out here, like shock going outside of the remnants. I won't talk about that here, but if you want to discuss, that would be nice on that topic. So the outline of the talk, after showing this brief expertise, is so a few words on supernova remnant for people here that are not familiar yet with supernova remnants. What kind of science do we do with Spectro-imagers, like Chandra, for example? And what are the challenges in this X-ray data analysis? And what are the usual analysis workflow that we use today to extract science from those observations? Then I'm going to dive into the details of this method. The key difference of this method is that we really work with the 3D cube XY energy instead of always making an image and then a spectrum and going back and forth between 2D and 1D. Here it works really considering the data as 3D. So what I will show you is how the benchmark that we did of the methods, and the application also to real data on the case of supernova remnant CasA and Perseus, and the perspective for Lynx and Athena. So why is it nice why study supernova remnant? The first thing, I guess, for me, originally as a grad student, what brought me to the field is that this kind of images, the most gorgeous image, and here you have plenty of gorgeous images in the corridor. And first, they are nice. And secondly, something that is interesting also is that they can evolve with time. Here you can see with that movie that the front shock that is here evolved like in a decade. And this is something that is rare in astronomy, to see extended sources like that moving in a decade or so. And this is one of the nice features object in which you can do that, and therefore you can measure the shock speed propagation. You can try to date those objects to know when the supernova exploded, etc. So that's already something to start with. And for those who are not familiar, in supernova remnant, usually you have different layers and different layers emitting X-rays. And the idea is that you have at some point the explosion, and this explosion releases a tremendous amount of energy that will create a shock wave propagating into the ambient medium. About, for example, for the young ones, it's about 5,000 kilometers per second. And you will have material from the ISM that is shocked to temperatures that will emit in X-rays. And you have, for example, different layers. You have the shocked ISM that is here. Then you have the ejecta that are shocked, that are shown in yellow. And then the reverse shock propagating inside that will hit the leftover from the star. That will transform the unshocked ejecta in the shocked ejecta here. And at the shock also, as you have this really high velocity shock, you can trap particles and accelerate them. And we believe that a supernova remnant can be one of the dominant source of accelerated particle cosmic rays in our galaxy. So there are all different reasons to study supernova remnant, and it's also something to tell you that there are different physical components in supernova remnants, and everything is then projected on the sky, and the game is to try to disentangle those synchrotron thermal components that we see. So going back to the beginning is spectro-imagers in high energy. So we are lucky in high energy to have spectro-imagers since the beginning. When I say spectro-imager, is something that can measure event by event and give you the position and the energy and also the time of arrival for different events. And this started really early in comparison with other wavelengths. And here at CFA, of course, was a front runner with different technologies and satellites in high energy. And so we can say maybe that spectro-imagers started back in the late 80s, but it really was a revolution when the CCD came, and that you could really measure more accurately the energy with ASCA in '93. And so really, for example, this is a schematic view. You have an X-ray photon that arrives here on the CCD, and for each of those events, you are able to measure the position of the incoming photon, the energy of that photon, and the time of arrival. So those are the main four information that you can record for each of those events. And based on that, you can make images, light curve, spectra, and basically you have those four parameters here, and you can make histograms in whatever dimension that you want. And so just to give you an idea of what the data look like, here is looking at the Chandra data of that specific pulsar, and as a function of time, the photon arrive, and this is the real data that I've used, and you can see that here you have the point source, this is kind of background, and here you have the PSF, and so this is the true nature of the data. They arrive, and we measure them, and we have a table of events. We call them events. They are X-ray photons for most of them, and this is how we start with the point sources. Then, what kind of science do we make with that? So we record those events, and then having a spectro-imager as an opposite to a collimator, where you don't know where the photons are coming from, you just record them, you can use that spatial resolution to isolate, for example, point source. And so you have a much better point source sensitivity if you're interested in detected faint point sources. Or if you're interested in extended sources, the idea is that you can use that resolution to isolate features in the image and try to study the composition, the spectral emission from this region as opposite to this region or something like that. So you can isolate features. And so this allows you, for example, to study spatial variation of physical parameters, like you want to study the temperature evolution in an object. And here is an example in the Perseus galaxy cluster, where here you have a temperature map, and you can see that you have colder regions here and that it's hotter in the outside. Or in the supernova remnant case, for example, you can study temperature, but you can also study the abundances, trying to go back to the abundances and trace the ejecta, the ejected matter during the explosion. And typically what you will do is, in those two cases, make small box, and in this small box, make a spectrum, fit it, and then derive physical parameters. So, but the problem with that, there is a challenge with that, is that, as I said in the introduction, for example, in supernova remnants, you have accelerated particles that will emit synchrotron, you have shocked ejecta, you have also shocked interstellar medium that comes at a different temperature, and so you have different components, and in the case of supernova remnant, the synchrotron is outside, the shocked ejecta is a little bit inside, but because of turbulence, this is mixed together, and sometimes, so you have these nested layers, but they are, because of turbulence, mixed together. And all of that is projected on the sky. Of course, through supernova remnant is a 3D object, and what we perceive is just an entangled version of the signal in 2D. And so that's the challenge, and in that kind of work that is shown here, whether you make this box a little bit larger or smaller will impact the abundance that you can measure. So there is an impact of how you define regions. And so there are different ways to do that. Usually what people do is to do some adaptive gridding that usually follows the brightness, for example. So each cell is defining on the surface brightness, and you say, I want to make size smaller when I have a lot of statistics and larger when it's fainter. But the problem on that is that the cell will follow the surface brightness, but they don't follow necessarily the physical components that are inside. So, and when you have everything that is nested like that, for example, the best cell definition to map the silicon abundances may not be the best cell definition if you are interested in synchrotron emission. And so you have something that is equal statistic, but it doesn't tell you whether this is adapted to disentangle physical components. And also, when you do that, it's a very painful analysis for people who have done that. You know what I'm talking about. You end up with 10,000 spectra to fit, and then when you compute errors, it's very long and problematic. But this is not the biggest problem. The biggest problem is that you are completely treating independently. Each cell is independent from this neighbor. So you are throwing away any spatial correlation between regions. And so what you do is you do a 2D job, and then you do a 1D, but you don't exploit the 3D nature of the data. And in the data, they are very rich. For example, in CasA, in the CasA dataset in 2004, there was a deep observation, more than 1 megasecond, and you end up with 1 billion photons in this data cube, 1 billion events. And how do you really truly extract the physical information that is in there? I think that by just doing this 2D, 1D step, you don't fully exploit the potential of the data. And so the traditional workflow, as I said, is, for example, you make an image, then you say, I'm interested in this specific feature, you make a spectra. This is not a real spectra, this is just a fake spectra to show my point. And what you will do then is go to XSpec and make a parametric fit, and you will say, I will compare the chi-square of just having a thermal emission model versus the chi-square of a two-component model. I look at the delta chi-square and I say, okay, this is significant, there is another component or not. And so all the disentangling process is done purely in 1D using the spectral signature. So what XSpec is doing here is that it's using the leverage that thermal emission have lines and power law don't have lines, but at high energy, the tail of the thermal emission and the tail of the power law, they kind of look a little bit similar. So you end up, for example, in here, in a degeneracy between the normalization of your power law and the spectral index of your power law. Because when the power law is here, you can push the normalization and decrease the index, or you can decrease the normalization and have something harder. So the two are degenerate here. And this is assuming that they have only spectral signature, but if you consider that they also have spatial signature, then you can lift the degeneracy between the components. And of course, in this case, the synchrotron emission is mostly outside, and the ejecta, for example, are mostly inside, so they don't have the same spatial signature. So you can use that in order to try to lift the degeneracy of your problem. So it's a bit of a kind of schizophrenia, and the real data are those ones, and in one sense, we project them and say, we work with 2D images, and on the other way, we say, okay, I'm going to look at the spectra, but we don't really use the 3D nature like that of the data. So the real nature of the data, as I showed at the beginning, is this 3D view XY energy, and this is just a visualization to show you the 100 kiloseconds or 150 kiloseconds of CasA in 2004, as a cube, and here you will see X, Y, and the other dimension will be energy, and this is what CasA data really look like. And so, but we don't usually work with that. We work with either a spectral on one side or an imager on the other side. And what's really interesting here is that here you see the spectrum of each different regions. And for example, here what you see the neon line, the magnesium line, the silicon line that are all here. You also see synchrotron emission. Synchrotron emission is this one that is flat here, that has no spectral signature. And for example, what is funny is that just looking at this cube here, you see the iron here, so that's the iron, and you can see that the northern part is redshifted and the southern part is blue shifted just here with the data. They don't lie in the cube at the same depth in energy. And this is only possible here because there is a very large delta V. And of course, if you have something that is 1,000 kilometers per second, given Chandra spectral resolution, you will not see it. But think of this movie with Lynx. This is going to be pretty impressive, where you could see all the spectral features moving like that in depth with energy. So, and above X-ray, I'm going to show here what we do in X-ray, but what you also do with Hess and what we do with Fermi. And so it's kind of a current status of the different analysis workflow that exists in high-energy astronomy. And mostly what we do in X-ray is this one. We say we make an image, then we make a spectrum, and we open DS9, we draw a box, and then we use that box to extract the spectrum, and then we do the physics within XSpec. And so usually the box are either drawn by eye or with this adaptive gridding that I showed at the beginning. And this is used both in X-ray. This is also used in Hess, where you define regions by hand and then you extract spectrum. And the issue is that, of course, in this specific case of this supernova remnant, there is a P-win inside. And when you extract the spectrum from here, in your spectrum, you will have a thermal emission from the remnant and a non-thermal emission from the P-win. And you have to do the job in XSpec trying to disentangle both with the problem that I mentioned before. Then in Fermi, what we do is kind of a 3D analysis, 2D, 1D analysis, in which you have the cube, the data cube from Fermi, X, Y energy, and you will decompose that as saying, so it's a parametric analysis, and you say that your cube can be described as a disk. Let's say that is a disk, multiplied by convolved by a spectrum plus this convolved by another spectrum. So it works fine with Fermi because Fermi has a PSF that is first highly dependent on energy, and also the PSF with Fermi has nothing to compare with X-ray PSF. So you can assume in Fermi that this guy is more or less a disk because the PSF. But imagine, of course, with Chandra, you cannot say that CasA is a disk. This will absolutely not work. And the problem here is that which morphology do you assume? None of the objects that we have are a Gaussian, a disk. This is the first order approximation, which is good when you have low statistics or when you have a very bad PSF. But for Fermi, it's okay, but and all of that, you have to assume parametric functions. And what I'm going to discuss here is this another example where we do a 3D, 2D, 1D approach, but it's a non-parametric approach in which you don't have to assume anything about the morphology, neither the spectrum. And so the idea is that you have those two components that are on top, that are nested, and that the algorithm will be able to separate them directly based on their spatial and spectral signature. So the idea came to me when going to a seminar in my lab, when there were people discussing about CMB and Planck analysis. And so in CMB, you have kind of the same problem. You are interested in the CMB, that is this very faint component that is here, and most of what you see is the galactic plane. And the game in Planck is to try to estimate the CMB that is in those crowded regions here. And most methods have a really hard time estimating a map of the CMB in the galactic plane here. Usually it's masked, and they forget about those regions, which causes problems in the power spectrum, because if you exclude some regions, then you cannot compute correctly the power spectrum for the larger scales. And so this group that was working on that proposed a new method in order to obtain a CMB map. And the idea is that CMB and galactic plane, they don't have the same spatial distribution, and they don't have the same spectrum. So the CMB has a very well-known spectrum, and the dust, for example, or the synchrotron have different spectral signature. So when I saw that, I realized that Well, this is exactly the same kind of problem that we have in X-rays, is that in CasA, for example, the synchrotron that is shown here in blue has the red spectrum that is here, and that the iron that is shown here and that is shown here, they both have a different spatial and spectral signature. And my job is to try to make a nice iron image or a nice synchrotron image and to try to disentangle everything that is that, deproject the data. So I wonder whether this could be applied directly to the data. So what we did in the last year was to start from the code that was applied to Planck and try to apply it to X-ray data. So of course, data are not the same in both cases. The first thing is that we have Poisson statistics, whether here it's additive Gaussian noise, and we have way more channels. In Chandra, you have 100, 300, 500, depending on the binning that you do, energy channels, and in Planck, it's 8 plus 1. And also something that is very different is that we have a very high dynamic range. Some of the features in CasA are extremely compact and bright, and so you have much higher dynamic range. And also, in the case of CasA, everything is more mixed together. There is no region or very little region on which you have iron alone, not mixed with something else. In the case of CMB, you have some large regions of the sky where the CMB is the dominant component and the galaxy is fainter. So that's another problem. So here comes the technical part. So the idea of this algorithm GMCA that is shown here, developed by Jérôme Bobin, which is in our lab, is the strong assumption underneath is that you can decompose a cube in a linear combination of cubes that are composed of a spectrum convolved with an image. So here the idea for the CMB is that you have your observations with Planck and that you can decompose that in saying a spectrum convolved with an image plus this, and so on and so forth. So with this, you can work in two different modes. You can say, I know the spectrum of the CMB, because the spectrum of the CMB is well known, it's the same everywhere. Give me the image associated to that. So you can fix one column in the matrix and try to estimate the column of here. Or something that is even more fun is you can say, I know nothing about the image, I know nothing of the spectrum, find me different components. And one of the limitations of the method is that it's true for the CMB, but in X-rays sometimes it cannot be true, that it assumes that the morphology doesn't change with energy, because here you have, your cube is just a spectrum convolved with an image, so you have the same image in each spectral plane. So at the beginning, when I look at the method, it kind of seemed a little bit like magic, where you don't fix anything and suddenly something pops out. And so where is the magic? What's the trick? And so in the method, you don't give any prior physical information. You don't give him anything. The method doesn't know anything about XSpec. It doesn't know the PSF. It doesn't know the response function. It doesn't know anything. And what you give as an input is a cube in energy, and the output will be n cubes. Each cube is an image, and n, the number of decomposed, is something that you fix by the user. And so when you think of it, it's kind of magic, but then if you make an analogy, it's not so magic, and we are used to it in a different application. It's the Fourier transform. Imagine here that you have a 1D signal, and you want to know what are the harmonics in there. And so basically, when you say that, you don't give anything about XSpec or any, prior physical knowledge, and all you have to do is to find a sparse representation, a better representation of the data in which the signal will be easier to disentangle. And in this case, in 1D, it's Fourier. So if you take this signal here, it's very complicated to tell how many components are there and to try to disentangle them. But if you project that to Fourier space, to frequency space, then you see that you have some spikes here, and you can see that those spikes are associated to different components. And here, it's a pure blind approach, and you specify nothing. And this is less surprising to us, and this is a little bit more surprising, but it's the same kind of approach. So in the case of image, what we use is not Fourier, but wavelet transforms. And this is just to give you an example on a CasA image of the wavelet transform. So the wavelet transforms give you different scales of your images. And what I'm showing here are the different coefficients of the different scales. So the first scale is showing you really the small features in your image, and then something at a broader and broader scale. And here, for each of the scales, it's the coefficient from all the pixels that are here, from an image that is dominated by the synchrotron and an image dominated by the iron. And the same thing as in Fourier before, you can see that here, red and blue are not at the same position. And if you look at the histogram, it will be easier to disentangle red and blue in this Fourier transform space than in the real pixel space. And if you use that at a multi-scale, so the first scale, the larger scale, and so on and so forth, you can see that within those 2 or 3 first scales here, you have enough information to disentangle them. If you go to the last scale, basically if you smooth everything, everything looks the same. So you don't want to use the larger scale because all components will look the same, but if you focus on the first scales, you can use that information to leverage the different components. So the algorithm is the following, in which you have this data cube here, and you're trying to solve this, in which you don't know A and you don't know S. If you don't specify anything, this equation has an infinite number of solutions. It's what is called an ill-posed inverse problem. And so you need to specify some extra constraint in order to solve the problem. And a quick example is that if you have 4 equals A plus B, and I don't say anything, there is no solution to A and B. But if you say A and B must be positive integers, then you end up with a much smaller set of solutions. And this is what we will do here. And what we do here is that we take each x, and x is in fact a 4D array because it's for each slice of the cube you make a wavelet at different scales. And what you do is that you impose sparsity in those images here, the same way that you will do in Fourier. You say, I want just as few components as possible in my Fourier spectrum. And so then what you do is that you estimate S for a given A and A for a given S. So it's an iterative algorithm like that, in which you can end up for A and S solution. At the beginning, you had no prior information on that. So to give you an example, before moving to supernova remnant, this is a very small example. Here you will see an animation showing each cube slice, where you have small Gaussians here, and there will be a larger Gaussian that will appear here. This is the spectrum of this simulated cube, where I have put a Gaussian, so it's a flat background here, and then there is a bump showing at some energy here. And those are the coefficients that I showed in the slide before for different energy. So in here, you will see the coefficient from this one that will be moving, and here it's the coefficient at a given energy here that will not be moving. And you can see that here, so here you see the Gaussian that appears, and when the large Gaussian appear, here at this energy, and here that's the wavelet transform of the third scale. So it's showing you larger features, and you can see that here, it's very not easy in the pixel domain to see the Gaussian appearing here, but in here, when you look at the wavelet coefficient, it's really clear that there is something popping out. And so, in a way, what GMCA is doing is some kind of clustering algorithm. You look at the wavelet coefficient and you try to find clustering in the wavelet domain in this data cube. And so it's some kind of unsupervised machine learning in which you don't tell anything, and it will try to find islands, clusters of pixels, and reconstruct images based on that. So once you apply GMCA to this movie that was before, this was the movie, and this is the results that GMCA found. So you can see that clearly it found very well the images, and those are the associated spectra. This is the total integrated spectra, and this large Gaussian is associated with this bump that is here, and the flat background is perfectly reconstructed as well. So you don't specify anything, and it saw this clustering and reconstructed the images. So now moving on to more astrophysical scenarios, what we did here is to make a toy model and try to mix stuff, unmix them, and see whether it was comparable. And so for that we used CasA data, and so we built a cube that was a synchrotron image here convolved with a power law here, then 2 spectral models. One, it's the same image, either convolved with a 2 keV thermal model or with an iron emission line, plus some instrumental background, and we end up with a fake data cube that is this one, in which, for example, you have the thermal emission, the synchrotron, and the instrumental background that is here. And the game is that you mix them, and then you unmix them, and just to give you an idea, for example, this is the synchrotron, and this is the thermal emission appearing and disappearing. And you can see that it's a rather small effect. I mean, it's not popping out super strongly. And the algorithm finds this. So it's able, this was the input, this is the output, this is the input, and this is the output. So it's very, very similar. And the game of the benchmark was to compare A and B and see if they were quantitatively similar. And so, up here. So first I'm going to show you the accuracy of the spatial reconstruction of the images, and we try to find some index. So people working on image reconstruction use this index that is a structural similarity index. Basically, 1, it's the same image, 0, it's absolutely not the same image. And what we did here was to compare, for example, for the model in which we add an emission line, an iron emission line, and you have the synchrotron that is here, the line that is here, and then we put the line fainter and fainter below the continuum. And this is what is shown here, line to continuum ratio. And what is shown here in red is the SSEM when you just integrate between two energies, and usually that's what, in several papers, that's what people do. You want an iron map, you just integrate between two energies and you get your image, but it's polluted in some way. And you can see that when you integrate the image, when the source is super bright, they look kind of the same because you're dominated by the iron structure. But then as you decrease as a function of this line to continuum ratio, the GMCA algorithm is capable of retrieving almost perfect images. And this one, of course, is starting to be polluted by the synchrotron emission. And this is an example here. This is the iron map. This is the same iron map integrated between two energy obtained in this point. And you can see clearly that here you see the synchrotron contamination, and here there is nothing. And in here, although it's much fainter, you can still reconstruct very well the iron structures. You start to have some noise, but you see some of the structures here. And the other question is, how well is it reconstructing my Gaussian feature, and what's the spectral accuracy? So what we did here is, again, the same game where you have a line and you're trying to draw it below the continuum, and you reconstruct, you go to XSpec, and then you reconstruct with the Gaussian the sigma, the initial sigma of the Gaussian and the centroid of the Gaussian. And you can see, and for each norm here, we did that 100 times, so that's why you have 100 points here. And you see that for very bright lines, you can reconstruct almost perfectly the centroid and the sigma, which is not a surprise. And then when you decrease and you decrease, there is a small drift, and that the width is underestimated a little bit, and the centroid is a little bit offset. But look at the axis. For something very faint, you have a wrong answer of 5 eV. And this is a Chandra spectral resolution of 100 and something eV. So that's really a small offset. And the same for the width. For fainter objects, you have a few 10 eV error on the estimate, but this is really small in comparison with what we can do usually. Now looking at the other model in which we have a synchrotron emission and we have a thermal model which will decrease in flux, and we look at the dashed line is the truth model, and the other one, the thick line, is the reconstructed model. And you can see that for very bright components, we perfectly reconstruct the spectrum, but then when we go down and down, we start to have an offset. You can see that the yellow here is very far away from the truth model, and after looking a little bit in detail, we realize that this is, so the synchrotron here, look, the synchrotron here is 2 orders of magnitude above the thermal model. So you're trying to reconstruct something that is 1% of the signal. And what we have, in fact, is that you have a leakage of the bright component that is the synchrotron that leaks into the fainter one. And this is, and also, it's also due to that both images are overlapping. If two images were perfectly not overlapping, then you will not have leakage. It's because the images are also overlapping. And what we found a way to solve this problem by adding a step that was not in the Planck version, because they don't have that kind of problem, is that we find in the image the regions that are strongly overlapping, and we mask them and in-paint them, in which we try to separate them as much as possible in order to reduce the possibility of leakage between one component and the other. And you can see, look at the yellow here. The yellow was way above the truth model, and with our new method, you can see that you can reconstruct, even for faint components. This is, again, more than a factor of 100 below the synchrotron component, but still you can reconstruct accurately the spectral value. So in order to apply that to real data, another question is, how do I estimate the errors? Because it's nice if I have a spectrum, but to go to XSpec, I need some error estimator. And unluckily, you cannot assume that your spectrum now follows a Poisson distribution, because as you have processed it and disentangled it, it no longer follows Poisson distribution. Because if you have 100 counts and now I have 70 counts and 30 counts, the Poisson 70 is not a Poisson distribution and 30 is not a Poisson distribution. The true Poisson distribution was the observed flux, but no longer when you divide it to small blocks. So we had to find a way in order to estimate the errors on the spectral model. And so what we did is the best way in the end turns out to be a bootstrap method, in which in the bootstrap you take all your event file at the beginning. Let's say that you have n events in your event file at the beginning. You will randomly draw n events from the n observed one x times. So you end up with x different event files that are randomly drawn from the original one. And then you run the analysis again x time, and you get x different spectra. And this is what is shown here. This is the error bar. So yeah, because in the toy model, we know the truth model in the beginning, so we can just have a true model, make a random Poisson of this true model, and do a Monte Carlo. And this is the true error bars. And what we compare here is the true error bar obtained with Monte Carlo with the error bar, assuming that you have only one realization of your true model, your observation that you got, and look at the errors. And you can see here, this is the one-to-one line here, and you can see that we get a pretty good estimate of the errors with the bootstrap method. It slightly overestimates the errors, but it's not completely unexpected. Having one realization is not as good as having the true model or having 1,000 observations. This is why it's good to have more observation time than less observation time, because you just want, you get closer and closer to the truth model. And we also tried in this paper method. In reality, I don't just have like a line and a synchrotron. The reality is more complex than that. So we tried with multiple components. And here you have a model in which you have the synchrotron that is shown here and two Gaussians that are very nearby and that you try to disentangle. And again here, the dashed line is the true model and the solid line is the estimated error by the method. And you can see that it's pretty accurate. And in this example, this was the centroid of both lines, estimated either by Monte Carlo or by Bootstrap. And you can see that this is off a little bit by 10 eV, plus or minus 2. So it's really not that bad in comparison, given Chandra's spectral resolution to be able to reconstruct those lines. And for each line here, of course, you have the image associated. That's what it's interesting. And in the other case here, let's say that you have a synchrotron emission and a cold plasma and a hot plasma. And we played the same game here, and you can see that the red one, the hot plasma, is well reconstructed. The blue one is a little bit offset, but in the end, in the temperature, we simulated something at 0.5, and we ended up with something at 0.4 keV. So it's not plus or minus 0.3, so it's not that bad as well. Then moving on to real life applications, that's the best thing, is looking at CasA. So CasA, as I said, is this gorgeous data set, more than 1 billion events in the megaseconds. And looking here at the high energy part, the 5 to 8 keV. So I start with the cube that is here, and then blindly I tell him, in that, I believe that there are 4 components. Find me 4 components in that cube. And this is what the algorithm will show you. So each time there is a spectrum, black line is the total spectrum from the input cube. Okay. And here you have the spectrum of this given component that is here. And so you can see that it finds clearly the synchrotron emission, the red shifted, the blue shifted component, and the last one is noise, which is telling you that you can also believe that when there is nothing, it will not create artifacts. When there is nothing, there will be noise. And looking now at each, applying the method around each line emission, so dividing the cube into small regions like that, this is what you will get if you make an interpolation around the line, and GMCA can do more than just an interpolation. I showed that it can recover the red-shifted and blue-shifted iron line, but it can also do that for all major emission lines. This is a map of the red-shifted and blue-shifted calcium. This is something I believe that was not really observed before, because it's a really faint line, and you can see that They share similar structure, but not exactly. So studying the evolution of the redshifted, this is going a step further will give you the 3D distribution of all the elements in CasA. That will be quite fantastic too. Right now we have that for the iron because it's the easy one, but we could try to do that also for all the different elements. So this was the high energy part, now focusing on the low energy part, and that's also quite interesting. It's much more rich and complex. And what the algorithm is finding, for example, it's still seeing the synchrotron below 2 keV. This is something that was never done before, also because you're dominated by the thermal emission. So you have a synchrotron map below 2 keV, and then it's finding different ejectas, layers. It's not only that they are redshifted, you can see it here, but also all the layers don't have the same ionization state and the same distribution. So I won't go into the details, but clearly this is something to dig into, to look at low energy, at not only the lines, but the different plasma conditions at low energy. A quick application also on that object that I showed at the beginning. Here you have the remnant, you have a pulsar and a p-win inside, and the algorithm tells you that here is the image of the p-win. You can see that it's a power law, and here is an image of the thermal, having subtracted directly also the p-win and the pulsar. Now going quickly to Perseus, that's also a fantastic result. Looking at the 1 megasecond of Perseus, those are the 3 main components that come out of looking at the low energy. And so this is basically the same image as Perseus. This is 90% of the photons end up in that image here. And then you see those 2 images that are very, very nice. And this one, I believe this is the X-rays, and it looks exactly the same as the H-alpha optical filament. So I believe that this is the first true image of the X-ray counterpart of the H-alpha filament, and that were buried. They are really hard to see because those regions here in yellow, we don't see them here, but they have like about 1,000 count. And look at the dominant here. Even the bright region here are 25,000 count. So you have to find 1,000 count on top of 25. So it's really good for looking at finding the needle in the haystack. And so the best thing is that not only do we have an image, we also have a spectrum. And so this is the spectrum associated to all the pixels that are here. And you can see, for example, some lines, some emissions. And so this is very preliminary, but this seems to be like a low temperature plasma here with relatively typical abundances for silicon emission line. So it will be the typical cluster gas that is infalling and that is in the associated with the H-alpha. And really, it's the first time that this component is isolated in the imaging and the spectroscopy, and we can constrain parameters that we will not be able to constrain before. The second part, this is the spectrum of this spiral here. So this spiral was seen in your simulations, and I took one of the time slice of your simulation, and it's really looking exactly similar to this one. And you expect in the spiral to have some colder gas. And here we have a gas that is about 2 keV, which is colder than the 6-8 keV that we see in the outer regions. And what's interesting is that it's mostly dominated by iron, and there seems to be very high metallicity from that sloshing front because it's highly enriched gas that comes from the core probably of the cluster that has been displaced by an impact and that now is sloshing around in the gravity potential in the cluster. And quickly, those components were a little bit seen in Andy Fabian's paper in 2006, where in each spectrum, this is one spectrum here, he tried to do a linear approximation, saying that the spectrum can be the sum of a cold one, a hotter one, etc. And what is shown here at the map of those weights, W1, W2, and you see that at low energy, there seems to be something here, but really the image here has nothing in compare with the image that I showed before. And the spiral here appears more or less also in the 2 keV component, and the temperature that I found was about 2.5 keV, so that's compatible. So the funny thing also is that really this sloshing front was appearing right in the data without doing any processing. This is the same kind of cube that I showed before, and look, the red part is in fact the spiral. The spiral is a low energy one, and so you see it directly. It's a cold one, so it's in the cube, it's showing at the beginning of the slice of the cube, and it was appearing without doing any analysis. If you use the 3D information, you can really disentangle components much better. So almost concluding here, so today we have Chandra and XMM, but with future instruments such as Lynx, it will really bring us a transformational view of the universe with having it's the dream machine, high effective area, subarcade PSF, and EEV spectral resolution. It's really the best you can dream of. But the question is really, once we have the data, what do we do? I mean, with data that will be so big like that, with about 10 billion voxels like that, how do you analyze a data like that? And we need to consider methods, not only the ones that are presented, but new methods that will explore the data in a cube way and not only 2D, 1D. It will be sad in 2035 to do a spectral analysis the same way we did with ASCA data. And so we need to find new ways in order to exploit the full capacity of those instruments. And so this is a quick simulation that I did with XIFU for Athena. And here it's a spectrum, red and blue shifted spectrum from iron. But instead of being minus 4,000 kilometers per second, here I did something much fainter, like close back together. And you can see that, so I constructed a toy model that consists of a red shifted part, a blue shifted part, but only 200 kilometers per second. And you can see that the method was able to reconstruct this red shifted part and this blue shifted part, and look at the precision. The spectral reference is in gray, and in red is what the method reconstructed. So you are almost perfectly able to reconstruct the spectral features. Even when everything is blended together, the method is able to disentangle them. So going to the conclusion, so I think that there is a huge amount of data in the archival Chandra observations, and the analysis methods, not all of them, but most of what we do are the same since the launch of the mission, or even in some cases the same as in ASCA data. And I'm the first one to blame. I've done that also for the last 15 years. But here it's a possible different approach in which you can use those methods not only for X-ray, it also works, for example, for any spectro-imaging instrument, such as optical, with Fermi, with CTA, and X-ray and gamma rays. It works so for extended sources, but it could also work, you can imagine doing a cube, not only in energy, but in time, if you want to see something moving with time. And we have proven with that paper, so the paper has been submitted by Adrien, and we get a good spectral and spectral accuracy, reconstructed accuracy with the method. We can recover really faint components, and we have found a way to estimate reliable error bars via bootstrap. And we have implemented an extra step to improve the spectral accuracy in the specific case of high dynamic range X-ray data, which is not the same as the Planck data. And I must mention that there are some, of course, some caveats, is that the method assumes that each component can be represented as a spectrum convolved as an image. So each image as the spectrum is the same everywhere around the image. And also the method is a statistic, needs a lot of statistic because you're working with the cube, so you need lots of photons to fill in the cubes. You have plenty of pixels to fill in. And from what I've tried, you need 1, 5, 10 million counts in order to start talking with the method. So not all the source can be applied with that method, but in the Chandra archive, there are plenty of extended sources where you have 1 million counts. Many bright sources have been observed 100, 200, 300 kiloseconds. And so definitely the method can be applied to multiple objects. And the perspective, so I've shown that there are really promising results on supernova remnant and clusters that the method can be applied to, revealing new features. And the development is not ending here. We have an ongoing development, and we are testing right now a Poisson version, because previously it was only assuming that the noise was a Gaussian noise, which when you have plenty of statistics, it can be approximated. And then something that is very interesting also, in some cases for faint signals, you want to inject some physics, because blind source approach is nice, but in some cases you say, I know the spectrum of the source that I'm looking at, give me the image, as such as in the CMB case. And so you can use this dictionary of spectral shape in which you will not give the definite spectrum, but you will say, my component follows a Gaussian distribution between 6 and 7 keV. I don't know the exact energy, but it should be somewhere like this. Find me a component that follows this law. And so this is what we are exploring right now. And something that I was wondering is that now that we have good images, spatial templates, we no longer have to assume that CasA is a disk, and we could use maybe those spatial templates to do a 3D analysis in X-rays. And I was wondering whether with Sherpa, whether that will be, how hard would that be? Currently, it's not implemented from what I read on the doc, but having like a Fermi-like analysis with Sherpa, and this will help to cross-check the spectrum that obtained with the method. And in the future, for Lynx and antenna, clearly we need to be thinking of new tools to fully exploit the wealth of the data. And I think following the 3D path is a good way in order to consider data as a whole and not only at 2D, 1D. And we could run benchmark on simulation, for example, as the quick one that I did for antenna. And the conclusion is really that archival data, Chandra data, and futurized spectral resolution, they are gold mine, but really, even if you're sitting on a gold mine, you still have to dig, and we have to find those tools to be digging. Thank you.
Very impressive. So, any questions for Fabio?
You mentioned wavelets. Wasn't quite sure where exactly they come into play. They use this wavelet. Do you use wavelet transform the spectrum or the?
So the wavelet is the analogy of the Fourier transform. Is that you could run the entire game in the natural domain, in the pixel domain, but you will not have enough contrast to separate the components. So it's wavelet. It could be something else. It just turned out that the wavelet are a sparse representation for images. And the nice thing is that with wavelet you have different planes, small scale, large scale, so it gives you a contrast between components. In the toy model that I showed, where you have small Gaussians and a large Gaussian, it's the best case scenario. All the power for one component will be in the third scale, and all the power for the small components will be in the first scale, so it's immediately separated.
Yes.
Another aspect of this method may be used to get the point spread function when the point spread function is not known or not very well known, as it varies. In the past, we have used blind iterative deconvolution to do exactly that. For example, solar images and other spectral interferometry and so on. So you can start completely blindly, but then you can put constraints. You know that the PSF is not infinitely large. You know there's difference of scales.
So in fact, yeah, that's something that the people who work on that were in discussion with some other team, and they wanted to use that in order to derive the spectral response of the instrument, which is the same if you do it in the PSF. So you can in fact blindly, you can say that instead, basically what I do is that I have a mixing matrix and I'm trying to derive the weight. In your case, the mixing matrix can be the PSF. And basically you have X equal PSF times signal, and what you're trying to estimate is both PSF and signal. It's the same game. So it will add. I haven't tried, but definitely. And if you know the PSF, for Chandra it's not so much of a use, but this method can be used to deconvolve the image as well. And for Fermi, this is something that will be very useful. And right now, people trying to do PSF deconvolution with Fermi, they work only on images. And so you have to have an image that starts, let's say, from 1 GeV to 100 GeV, and within that the PSF changes, but you don't. So you take a mean PSF, and you have to remove all the low energy because the PSF varies so much that you cannot have a mean PSF. But with this method, you can do 3D PSF deconvolution having the true PSF, and I think this will be much more powerful to do a deconvolution using the cube than just using an image again.
And also, even for Chandra, you're limited by the goodness of calibration.
Yeah.
With this, you can improve on that because the data will tell you.
Yeah.
So you can get even higher resolution.
Yeah.
Than what you get now.
It could be better. In the end, whether it will be better or not, we don't know. But in theory, yes, I agree that it should be. You need high statistics, of course, in order to do that. But there are many sources in which you have point sources in which you have tremendous statistics, in which this could be tried.
Yeah, I'm not sure I understand the technique exactly, or I'm missing something. So my question may be stupid, but so in the case of whether you have a missing component in your model, when you have let's say 4 components you're trying to iterate, and then how does it look like if you are missing some component? It'll say some iteration doesn't converge, or
so imagine that in my toy model I injected 2 components, and I asked So let's say I injected 3 components and I ask 4. That's your question. Or I
Or
ask
I
2.
ask 2, and then how it looks
Okay,
like, whether
so-
it overfit or.
So I tried that. We tried that. For example, one example is in the toy model in which I do synchrotron, redshifted, blue shifted. If I ask 4 components, I have noise, red, blue, synchrotron. So that works. If I ask 3, I have a little bit noisier red, a little bit noisier blue, and synchrotron. If I ask 2, I have iron that is mixed between red and blue. Red and blue are compacted together and synchrotron.
Okay, so in the case of spectral fitting, a very primitive technique, you can say chi-square is not close to 1, reduced question, so there must be some additional component.
Yeah.
Here, could it tell you are missing some component, or?
So that's a good, there are 2 answers to that. One of the questions of the referee from the paper that we had was, can you fix automatically n the number of components automatically within the method?
Yeah.
The answer is that mathematically you can, but it's very complicated and very slow. The other answer is you could get, because in the end you have x, your data, and you're trying to decompose that as a and s. So in the end, you can, basically what the algorithm is trying to minimize is x minus as. It's the norm, the chi-square of x minus as to converge towards something. So you have some kind of estimators in that, but you can also at the end compute the likelihood of a and s and see, and try different combination and see whether which one give you the best likelihood. Or something that I did mention also is that the algorithm is really fast to operate. Like to analyze a cube that is 256, 500, it takes 10 seconds or something like that. So you can try different components, 3, 4, 5, and when you start to see noise, basically what we did is that we do, well, doing one component doesn't mean, but let's say that I injected 3 components, I do 2 components, I have something, I have 3 components, I have a significant new one appearing, I do 4 components, I have noise, I do 5 components, I have noise, I do 6 components, I have noise, and at that point you can say, okay, stop here because there is nothing new appearing.
I wonder if you found any failure modes when you run experiments, like when an algorithm found structures or separated into components which did not exist.
So that's so on one of, so we try to crash the algorithm as much as possible. That was the game of the benchmark, and there was no case in which the algorithm created an artifact. So in the case of exactly this, when you have more components or you play with different things, it adds you some noise features, and so there is no really artifact like that, which we managed to fool the algorithm in a way when you have images that are too much overlap. For example, if you take the synchrotron and the synchrotron, but you just apply a Gaussian on it, so it looks exactly the same, but the brightness is a little bit fainter, etc., then it mixes them, it cannot separate them. And so it really needs to have, like, this is a good case with Perseus, for example. Those 2 components are, like, this is a large scale component, is very different from a filamentary component here. And so this works best for the algorithm. Then disentangling this one with this one that will be a little bit brighter here and here, it will have a hard time figuring out. You have to think of it in terms of clustering. In some space, in some complicated space for our mind, which is the Wavelet space of a cube, so a 4-dimensional array, these clusters live not in the same position as this cluster of pixels. So this is where the algorithm is the best at. But I'm sure that there are some cases in which, an answer to the question is also, not seeing a feature doesn't mean that it's not there. It means that the algorithm is not fully operational in this specific configuration. So setting up a limit on a thing that you think is there but it's not there is not super trivial.
I have one more question to ask.
Yeah.
So speaking of looking for a needle in a haystack, this is of course of self-interest. But how efficient is it to find faint features like 3.5 to 11?
So blindly, if you try, so yeah, if you, it works well with features that have a significant signature, as I said, special signature. This has a very strong structure, and we don't know what's the image, what's the spatial distribution of this this line. But if you imagine that this is a beta model, it's something that will be smooth, a smooth variation transition. It will not be easy to detect it because in the wavelet domain it will be maybe completely washed out, or it will not have enough power. One thing that could be tried is that exactly like the CMB, instead of being completely blind, you can say, I know the spectrum, give me the image. This might work better. And for filter lines, you need to go to the Poisson mode because if you have faint statistics, assuming that you know the illusion is no longer a good approximation and you end up with problems. So it could be tried with this Poisson GMCA version.
All right. There are no other questions, then let's thank Fabio again.